Good afternoon, students. Myself Pragnesh Polara from Om Engineering College, Junagadh. Today we are met here to discuss some frequently asked examples from the applications of partial derivative. So today we will quickly look at some most important methods related to which example frequently asked in previous year's GTU's exams, which are very most important methods. Just look at the PPT here. We have already learned about some applications of partial derivative. Today we will discuss some topics, examples related to which frequently asked in GTU exams. So first we look at examples related to find tangent, plane and normal line to a given surface. We have already discussed in the previous sessions that how to find tangent, plane and normal line to a given surface. Then to just recall the formula of tangent, plane and normal line for a given surface, and then we will look at the examples which is asked in GTU exam. Let us look at the formula for tangent plane. Here equation of surface if is for example f of xyz is equal to 0, and we want to find tangent plane at the point x1 y1 z1. Then equation of tangent plane is x minus x1 into del f by del x at the point P plus y minus y1 into del f by del y at the point P plus z minus z1 into del f by del z at the point P is equal to 0. So if we want to find the equation of tangent plane, we need to derivative the given surface plane, surface f, or with respect to partial derivative with respect to x at the point P, then partial derivative of f with respect to y at the point P, same way for the z, and putting all this value in this equation, x minus x1 del f by del x plus y minus y1 into del f by del y plus z minus z1 into del f by del z is equal to 0. This is the equation of tangent plane. In the same way, the equation of normal line is x minus x1 upon del f by del x at the point P is equal to y minus y1 upon del f by del y at the point P is equal to z minus z1 upon del f by del z at the point P. So using this formula we can find the equation of normal line to the given surface f of xyz is equal to 0. So this is the formula to find tangent plane and normal line. Now let us look at one example to find in which we will going to find the tangent plane and the normal line for the given surface. Let us look at the example. Find the equation for tangent plane and normal line at the point 1 1 1, which is our x1 y1 z1 on the surface x square plus y square plus z square is equal to 3. This example is asked in January 2010. Okay, so this is most important example, but this method is most important for the exam point of view. Here the solution, here f of xyz is equal to x square plus y square plus z square minus 3 is equal to 0. This is our surface, and our point, and the point x1 y1 z1 is equal to 1 1 1. Okay, now first we will find del f by del x. Del f by del x is equal to 2x very quickly. In the same way, del f by del y is equal to 2y, and del f by del z is equal to 2z. To find the tangent plane and the normal line, we need to find the partial derivative of x, of f with respect to x, with respect to y, and with respect to z, but at the point x1 y1 z1. So now we need to find del f by del x at the point x1 y1 z1. In the same way, del f by del y and del f by del z. So if we put here x is equal to 1, then del f by del x at the point P is equal to 2. In the same way, del f by del y at the point P is equal to 2, because y is also equal to 1 and z is also equal to 1. So del f by del z is also equal to 2. So we get del f by del x, del f by del x is equal to del f by del y is equal to del f by del z. All are equal to 2, implies equation of tangent plane is x minus x1 into del f by del x at the point P plus y minus y1 into del f by del y at the point P plus z minus z1 into del f by del z at the point P is equal to 0. So here x1 is equal to 1, y1 is equal to 1, z1 is equal to 1, del f by del x is equal to 2, del f by del y is equal to 2, and del f by del z is equal to 2. So we will get x minus 1 into 2 plus y minus 1 into 2 plus z minus 1 into 2, z minus 1 into 2 is equal to 0. So after simplifying this one, we will get 2x minus 2 plus 2y minus 2 plus 2z minus 2 is equal to 0, and simplifying this equation, we will get the equation of tangent plane. So using this method, we can find the tangent plane. Now we are here to find tangent plane and normal line. So we have already find the equation of tangent plane. Now we will find the equation of normal line. Okay, so let us look at the normal line. So equation of normal line. Equation of normal line is equal to x minus x1 upon del f by del x at the point P, y minus y1 upon del f by del y at the point P, and z minus z1 upon del f by del z at the point P. So here the equation is x minus 1 upon 2 is equal to y minus 1 upon 2 is equal to z minus 1 upon 2, which is also written as x minus 1 is equal to y minus 1 is equal to z minus 1. So this is the equation of normal line to the given surface. So this is very most important method, using partial derivative to find the equation of tangent and normal line to the given surface. So this is the first very most important part of application of partial derivative, how to find tangent planes and normal lines for the given surface f of xyz is equal to 0. Now if we look at the PPT, then next very important application of partial derivative is to find the extreme values of given function. That means the maximum value and minimum value of the function. In this section we will learn how to use partial derivatives to find local maximum and minimum values of the function with two variables. So I am not going to discuss the primary things, but I am going quickly to the second derivative test, using which we can find the partial, we can find the maximum value and the minimum value of the given function. Okay, so this is the second derivative test. The second partial derivatives of f are continuous on a disk with center AB. Then if we take the partial derivative of function at the point AB with respect to x is equal to 0, and partial derivative of f with respect to y at the point AB is equal to 0, that is AB is a critical point of f. Okay, then if we take d is equal to d at AB is equal to, this is the test that if d is equal to fxx into fyy minus f of fxy square, all at the point AB is equal to d, and if d is greater than 0 and second partial derivative of f with respect to x is greater than 0, then f is local minimum at the point AB. If d is greater than 0 and fxx is less than 0, then function is local minimum. If d is less than 0, then f of AB is not a local maximum or local minimum. And in case C, we can say that the point AB is a saddle point. That we already know that if at the point AB function is not maximum and not minimum, then we can say that the point AB is a saddle point. So this is the second derivative test. If d is equal to 0, the test gives no result, means we cannot say the f could have a local maximum or local minimum at AB, or AB could be a saddle point. So we cannot say anything about the maximum or minimum value of the function if d is equal to 0. So this is the easier method to remember this theorem, or we can say this formula for d. D is equal to fxx into fyy minus f of fxy square. We can put it in the 2 by 2 determinant by fxx, fxy, fyx, fyy, and by solving by expansion of this 2 by 2 determinant we can find the formula of d. Okay, so now look at the example about to find the maximum and minimum value for the given function. Okay, let us look at one example. The question is find all the locals find all local maxima and minima and saddle points of functions of a function fxy is equal to x square minus 2xy plus 2y square minus 2x plus 2y plus 1. Okay, this example is asked in GTU April 2010. Here we need to find the maximum and minimum values of this function f of xy is equal to x square minus 2xy plus 2y square minus 2x plus 2y plus 1. Okay, so first we need to find f partial derivative of f with respect to x. That means fx is equal to, from this equation we will get fx is equal to 2x here minus 2y, this one is equal to 0, this one 0, this one 0, minus 2. Okay, 2x minus 2y minus 2. Okay, then in the same way f of y is equal to here minus 2x plus 4y, from here minus 2x plus 4y plus 2. Okay, so this is the partial derivative of f with respect to x and with respect to y, and if we take f of x is equal to 0 and f of y is equal to 0, we will get 2x minus 2y is equal to 2, and we will get minus 2x plus 4y is equal to minus 2 by